In this lecture, we will be taking a closer look at chemical processes of rock weathering and specifically looking at a very unique terrain and distinctive landscape that is the result of, in this case, weathering involving aqueous solutions below ground. I'm describing for you in this case the development of a karst topography. The term karst in this case is of Slavic origin, and it is applied to a variety of below ground landforms as well as the unique processes, again those that are associated with chemical weathering specifically, that are in a sense responsible for these below ground environments. To understand the nature of karst and how it develops, and karst in a sense as a kind of unique natural process, we have to understand something about hydrology. We have to understand something about the nature of bedrock within these developing karst environments, and we have to understand something about the structural nature of the rocks themselves. Take a closer look at this diagram. The content of the diagram will be helpful in terms of understanding the wide variety of expressions that exist within a developing karst environment. It will also provide you with a lot of the common physical traits, terrestrial traits and subterranean traits that geologists look for when they are classifying and categorizing a particular local landscape as karst. As you closely examine this diagram, I will give you some additional information regarding the content of a karst environment. So let me begin with some of the basic concepts. When we talk about a karst landscape, what are we talking about? We're basically talking about a limestone landscape environment, and one that generally will develop below ground. Now, limestone is probably one of the most abundant bedrock types on the face of the planet. As you know, limestone is a kind of non-clastic sedimentary rock type. Generally, the contents, physical and chemical contents of a limestone type will generally be laid down through solution. It's usually a low energy environment where chemistry is precipitating and where we are starting to get deposits that eventually lithify. Local limestone landscapes are highly susceptible to chemical weathering, and they are so because of their chemistry. Such weathering creates very specific landscape components such as pitting, very bumpy surfaces, so we see a great deal of very jagged undulation to the land, and also we see an environment that is characterized in terms of the landscape by poor surface drainage and very well developed below ground water channels. There are four basic characteristics that I'd like you to get into your notes having to do with karst topographies, and I'll take you through each one of these. Basically, they are a kind of recipe for the development of a karst environment. Number one, the limestone that forms the regolith, or the parent resources for local geology and soil materials within this environment, these must be at least 80 or more percent calcium carbonate in terms of their overall makeup. So the limestone itself has to be a big part of kind of the underlying parent material for this developing landscape. Number two, there must be complex patterns of rock joints above and below ground. This will allow groundwater the ability to form subsurface drainage systems and potential subsurface areas of weakness that, and again, weakness being expressed more in terms of surface area, weakness that can be then interacted with through a process of chemical weathering. Third, there must be an aerated or air-containing expression below ground, or a strata that is air-containing. This will be very, very important because, again, we need the movement of water from the surface down into the local groundwater table environment. And this further ensures water is going to intrude and allow for chemical weathering to occur. So let me restate that again. Uh, there is a third characteristic that's important. We need a nicely defined zone of aeration, or we need strata within uh, this region, within the profile of a developing karst environment that will be air containing. It will allow water to move down from the surface as it approaches the groundwater table, and it will also allow that water to begin the process of chemical weathering as it interacts with the soil and then eventually the regolith that is part of this eventual subsurface landscape. And then we also need vegetation. Vegetation must be present at the surface. And some of the most key expressions of vegetation communities that are contributing to a developing karst environment can be found in this case, wetland environments. And you can see that also being expressed in this hypothetical um, or modeled diagram of the bluffs surrounding what is today the Green Bay area of Wisconsin. The vegetation is important because it represents another important source for organic acids that will act as catalysts as the weathering process begins and then as it continues. The last thing that I'll have you look at with regard to the diagram is, in this case, what's unique about the surface as it relates to the developing karst topography below it. Very often, one of the key surface traits that we associate with a karst environment are the development of sinkholes, or these circular surface depressions that result from below ground collapses of limestone layers. Now let's take a closer look at the process of chemical weathering as it relates to a limestone environment. To a lesser degree, we can see the same kinds of chemical weathering affecting even sandstone and other um, bedrock or geological deposits that have even clastic particles as part of their overall physical makeup. In this case, the key compound is calcium carbonate. It's a quality of bedrock in most, if not all, karst environments, which directly speaks to the landscapes and their susceptibility to chemical weathering, or to an environment that is very acidic with regard to groundwater and groundwater movement. This process of chemical weathering is also referred to as carbonation. To a degree, the weathering process as it relates to a developing karst environment is occurring below ground. It can be fairly shallow in terms of where this chemical weathering begins, or where we can initially measure it, but it can also have significant depth, reaching, of course, bedrock and impacting even, in this case, meters within that bedrock environment. What this is a kind of fluvial action. So a lot of what we have looked at regarding fluvial processes are going to be helpful in understanding how a karst landscape develops, and even being able to predict how that same below ground landscape will continue to develop over time. Fluvial action in this case is going to impact subterranean environments. The initial understanding that we have of flow as it relates to limestone landscapes and their chemical weathering is generally measured in terms of primary porosity of the bedrock itself. So geologists will generally start their study of a karst environment by looking at the physical makeup, the mineralogy of local bedrock, and they'll specifically conduct experiments that will closely examine the porosity of that particular local bedrock type. When we're talking about porosity, generally we're talking about the amount or the overall volume of voids or air spaces or space for any sort of gaseous material to inhabit that exists within a body of rock. A secondary measure or a second thing that geologists will address is or can be further labeled as effective porosity of a bedrock type. This is the um, estimate of the degree of connection between voids that make up the overall primary porosity of the rock itself. So this effective porosity does connect to that primary porosity, but it looks at how the internal order of spaces is interacting with one another. Again, further assessing how and how quickly, how much and how quickly we will find water or any sort of solution, aqueous solution, flowing through the rock itself. Here in Wisconsin, our local dolomite is a unique expression of limestone, but you will find that it will not be as reactive for many of the major acids that are part of this process of chemical weathering. However, things like hydrochloric acid will definitely demonstrate some sort of carbonation as it relates to dolomite. But dolomite will not be as susceptible to weathering when we compare its interaction with compounds that include sulfuric acid, for example. So our local dolomite is unique. In a sense, it is less susceptible to internal weathering, really because of its intercrystalline nature or intercrystalline structure. It has a very tight structure, and it doesn't allow for as much of this effective porosity to develop as it lithifies. So the dolomite represents, I would say, more of the resilient kinds of bedrock types as they relate to karst and karst landscapes. And when we compare this intercrystalline structure for dolomite, for example, at least a Wisconsin expression of dolomite, if we compare it to other forms of limestones or even related lithified sedimentary rocks such as sandstones, we can see that the internal cavities are more elongated and often express smaller measures of effective porosity, again, when we look at a dolomite type, and especially the kind that we would see in, let's say, Door County or anywhere along the eastern shoreline in some of those expressed bedrock or outcrop environments along the shore of Lake Michigan. It acquires this internal structure really from chemical compaction that occurs during the lithification process. And as even the calcite, which is such an important base element for dolomite, as that precipitates out of water. So it's a very unique type of in this case, sedimentary rock, non-clastic sedimentary rock. And the timetables, the scale for any sort of developing karst topography as it relates to dolomite is much more elongated or long-term than what we find with other, in this case, more rounded crystalline structures in other limestone deposits and limestone deposits that have a less hardened kind of expression to them. Finally, we have secondary porosity. As limestones age, they will begin to express an increasing measure of this porous type. Generally, secondary porosity relates to the cracks and weaknesses that will develop in terms of the internal structure of local bedrock within a karst environment. As these cracks and weaknesses begin to develop, fluids will travel along these areas of weakness, again, moving into these kind of low energy environments and more channelized environments. And this is where we start to see some of these very dramatic cave-like
developments begin to occur below ground. And so this is another measure that geologists will make as they look at the overall development of a landscape, its secondary porosity, just above and then within the water table itself. Let's talk a little bit about the water table as it relates to a karst landscape. In limestone hydrology, the term Vadros zone is usually applied to the rocks and soils that are situated above the water table. We will see signs of, in this case, chemical precipitation and chemical weathering in this Vadros zone. But then we'll also see probably the most extreme forms of chemical weathering and the most dramatic aspects of our developing karst landscape occurring just below this, or in this case, at and below the water table itself. We would recognize this subterranean environment as being a zone of aeration when we're talking about the Vadra zone in terms of flow or subsurface or surface runoff, and how that process of surface flow and initial below ground flow of water is interacting with local expressions of groundwater. Below the water table, and especially in a limestone subterranean landscape, we have what is referred to as a phreatic zone, similar to a zone of saturation within soils or even glacial soil environments. This zone is completely filled with water at the time it's being identified. Of course, over time, as the water table fluctuates, as groundwater begins to move throughout the developing karst landscape environment with new voids and things like that. In the regolith, this geographical location may change as well. Now, there is a mathematical principle that we have to account for in relation to this phreatic zone. It provides us with pressure forces that directly impact the weathering of local limestone and the sedimentation that will eventually lead to more resilient expressions of lithic materials such as dolomite. So one of the things that we have to start taking into consideration as we move to and then below the water table is, in this case, water pressure and even terrestrial and soil expressions of air pressure within a study environment, in a sense. And the other thing that I mentioned, but I really want to mention it a second time, is that remember that as these karst topography or these karst landscapes develop, what is being removed chemically from these environments and then later deposited in a low pressure environment, as it lithifies, if that's ultimately what happens to it as a developing landscape, it will express a much more resilient intercrystalline structure. And so, again, the dolomite that we see throughout portions of Wisconsin, and especially along that kind of eastern edge of the state, these are all things that would have developed in a kind of secondary environment where they would have, in a sense, been eroded from a limestone parent type and then deposited at a later time in solution. So when we look at intercrystalline structure and how it is deposited, we can really get a sense of the overall landscape history and erosional history of a much larger regional environment. Let's take a look, or take a closer look rather, at this concept of pressure, and then we'll eventually connect it to ideas having to do with hydrology and the work of a 19th century French civil engineer, Henry Darcy. The pressure that exists within these watery environments generally will be equivalent to local measures of air pressure at the surface level. Now, as you know, seasonally, in terms of weather patterns, and then of course long term, even in terms of climatic shifts within regions, and of course the air masses that are associated with weather and climate. As these additional variables begin to fluctuate, expressions of air pressure will also fluctuate with them. Some are more predictable than others, but many of them are very chaotic in nature. So as you are taking into consideration what's happening below ground, and as you are incorporating, in this case, local air pressures, you have to look at them in terms of when you are collecting your data, or the period of time at which you are collecting data. So we have air pressure, and we have a situation where we need to add to this pressure estimate the overall measure of how much water is within the area that we are studying. So we have air pressure, and then we have a ratio that initially we will use as we assess what stage or how rapidly a karst topographic environment is developing. We will take a look at the volumetric weight of, in this case, zone water. So we can take a look at that phreatic zone. We can look at how much water is present in our project area below ground, and then we can determine a volumetric weight. We can compare that, or we take that into consideration with local expressions of air pressure as we are beginning to determine how quickly this chemical landscape is developing. Now, volumetric weights for these zones, specifically the zone below or at the water table, they are estimated in terms of kilograms per square centimeter. However, we will also see these estimates being converted to pounds per square inch, or PSI. These converted PSI units, pounds per square inch, are then added to the air pressure that is present at the moment that these studies are being conducted. So just to review a little bit here, we're taking into consideration the overall volume of water that is within an environment. We're comparing that to local expressions of air pressure. Then we're also taking volumetric weights, those same weights for those phreatic zones, and then we are also creating an additional variable where we are adding local expressions of air pressure at a particular moment in the annual calendar. And so we're using these two variables to get a sense of how rapidly the developing karst environment may be occurring. Basically, what are we doing? We are incorporating hydrostatic pressure as a measure of force in our understanding of how a terrestrial landscape is developing and how much of the local air mass above this developing environment, and really that what we find at the terrestrial level, what expression of that local air mass is part of our understanding of where and to what degree this developing environment is occurring. So this pressure can be significant. I mean, these are pretty large numbers. Thousands of pounds per square inch are what generally hydrologists will measure these units in. And they will ultimately incorporate the depth of the water table. They'll incorporate the thickness of the water zone, and they will also take a look or consider the overall elevation above mean sea level, depending on where the landscape is, in terms of where that water table is. So all of that is considered as these estimates are made, and as you can imagine, the numbers are significant. They're massive, and the results of this process are also, large in scale. We're not talking about anything small. We're talking about literally, hundreds of square miles of below ground or subterranean environments that are being modified by this chemical weathering and all of the variables that surround it. As we are trying to understand how and why a particular subterranean environment is developing, we have to incorporate many of the same kinds of measures and equations that we utilize when we are looking at a system of flow. And one of the most important mathematical principles that we will incorporate it into our understanding of a developing karst environment is Darcy's law, or the work of Henry Darcy. Why is this important? Well, generally, when we're talking about Darcy's principles, we're really talking about how water within a system, it could be closed, it can be open. Generally, his system, when you look at it a little more closely in terms of an experimental system, was open. How water is flowing through this, he incorporated a medium in his assessment of water flow as it relates to something like a change in elevation. So again, when we look more closely at this, what you'll see is that within an experimental environment, Darcy will incorporate a medium like sand. And he'll have a specific volume and area that he will associate with that material environment. And he will then factor in how water is flowing through that environment and forces of gravitation, for example, as they relate to elevation change, how those are ultimately part of the process. And then the overall weight of the water itself at a starting point and an end point in his experimental design. And when you take all of this into consideration, it really represents an ideal model for being able to understand what's happening below ground as it relates to flow in a karst environment. So as I already mentioned, Darcy's law is a principle, a mathematical principle that was established by Henry Darcy. He was a civil engineer, French civil engineer, who lived between 1803 and 1858. He calculated water pressures for supply lines in and throughout the French countryside. As Darcy was designing systems for delivering water in and throughout the French countryside, he realized that he could predict discharge rates by regulating input, things like pipe diameter, and of course distance over which water was flowing. He was also able to, in a sense, incorporate elevation changes in this process, and he was able to estimate where recharge could be set into the system so that additional waters could be more efficiently incorporated into a utility environment. So his work, his engineering as it relates to providing 19th century French families with running water was really perfect for understanding how the natural environment, in a sense, supplies water even below ground. Now, a very important component within Darcy's principle is this idea of hydraulic conductivity. This is the volume of water that exits or flows out of a system of flow each day. So it'd be generally measured in square meters per day. Now, in a karst environment, this discharge would be, in a sense, at lower elevations or at the lowest elevation within a select area. It would be the point, in a sense, where the water table intersects, for example, a body of water, exposing the water that is part of this system of flow to the lower atmosphere. So for a geomorphologist, physical geographer, hydrologist, and geologist looking at how and why a karst environment is developing the way it is, elevation becomes a real key measure in incorporating the Darcy principle in his or her overall understanding of this developing environment. In this case, when we're taking a look at Darcy's law, the math that is part of this process, and one or even several of the experimental models that have been applied traditionally to the work of Henry Darcy, we can see a variety of factors at play, and I'll just highlight a few of them in terms of the importance of what we're looking at here and in relation to the karst landscape. So ultimately, our kind of end um, point is the equation itself, and there's a variety of variations of this equation, but here's some of the general principle. When we're looking to establish Q, we're looking to establish the total discharge for our system as it relates to again, the volume of water at specific times of year that are flowing through a landscape. And generally, this will be measured in square meters per second. So it will take a look at how much water is flowing through a system, and it will be the square meters of material that are moving through that system each second. In a sense, what is it take into consideration? Well, it's taking into consideration the total pressure that is within an experimental environment and how pressure is diminishing as we move from an area of higher elevation to the, let's say, left of the diagram to an area that is of lower elevation on the right-hand side of the elevation or of the diagram. And this pressure generally will be measured today in pascals. What then do we examine this change in pressure in relation to? We change it, or we examined it in relation to the overall length of a medium that the water is moving through. This is sometimes referred to as a dynamic viscosity measure. It's the length over which the pressure drop is taking place and that the water is moving, again, from a place of higher elevation to one of lower elevation. Other parts of this equation that become important, when you see the letter K, this represents the permeability. It's a coefficient having to do with the permeability of the material inside of our experimental model. And then A, of course, is the overall area through which the water is flowing, and it is ultimately the area, the total area of our experimental space, right? It's how much medium, right, in terms of square meters, is present in this experimental model. So it's really a fascinating design when you take a close look at it, and it really does help us to understand how water is going to, in a sense, flow through an environment. Now, if we take a look at two additional pieces of the equation here, K and A, in a natural environment, K is going to be a ratio of the length of flow and the range of elevation between a point of input and a point of output. So in this case, the length of flow and the change in elevation between a high elevation and a lower elevation within a developing body of water or system of flow. In Darst's experiment, or Darcy's experiments rather, K would have been usually a coefficient that also included the medium that he was kind of sending the material through, but it incorporated both of these qualities as well. And then of course A is the overall area, the below ground area through which the water is flowing and within which the chemical weathering is occurring as it relates to the flow. Now, what did Darcy find as he began to apply some of these experimental models to the natural world? He found that as the length of flow increases, the length of flow between areas of recharge or an area of input and output, the discharge will correspondingly decrease. So he found that the length of flow as it increases, the discharge will correspondingly decrease. And this decrease is predictable in relation to the thickness of flow, or in the case of Darcy's experiment, the overall diameter of the tube carrying or the pipe carrying the water. So a couple things just to review here again. He found that the length of flow as that increases, the discharge from the system correspondingly decreases at any one given point, and that the decrease is predictable in relation to the overall thickness of the flow or the diameter of the pipe carrying the water. Now, what this does for us as physical geographers, as in this case geomorphologists, is it gives us, in a sense, a mathematical principle for understanding discharge throughout the entire system, especially between points of high energy and low energy. It also tells us that the amount of water that is flowing through a karst environment, through a subterranean environment, is proportional to, in this case, the overall area, the overall size of the landscape below ground that it's moving through, and again, the difference in elevation between any two given points. Finally, it gives us a better sense of hydraulic conductivity uh, in a natural environment as opposed to a laboratory or experimental environment. Again, K, the idea that the length of flow and the range of elevation between an area of input and an area of output is important, and it's something that we can estimate and connect back to the overall discharge of this below ground system of flow. So what I'd like you to do is just to review this material and keep Darcy's experiments, his principle, his law in mind as you are wrapping your head around the process of below ground chemical weathering and some of the important variables, some of the important factors that we have to consider, that we have to record as we are attempting to apply things like slope and hydrology to our understanding of water as it moves toward and throughout a below ground water table environment.